is a wooden stone tool. It is made out of wood, so no matter how many times we're not using it, we just bring it out to use it, and the idea is that the wood and the glass never actually touch each other. There's a thick layer of steam between the two materials that the glass is riding on. We're going to get a quick starter bubble on this. We're going to get our starter bubble, and then we need a little bit of pressure. So we blow into the pipe, and then we cap it with our thumb, and the bubble expands in the weakest point, which is the glass, and not the steel pipe. Now that we've got that starter bubble, though, it'll be a lot easier to add air here on out. Those wooden tools that we keep back there, those are specifically for woods. These ones are cherry wood. It has less sap, so it doesn't leave a residue on the glass if it does touch the glass. But sometimes it does steam evaporates. Also has a tiny break burns a lot. It's using this time to let the piece cool down a little bit. So we're going to go in and get a second layer or a second layer of glass over this. Just using this time to think ahead. We're always thinking a few steps ahead of glass blowing. Getting the tools ready, making sure we're ready for this next step. Then the first layer is cool enough and hard to solidify to be able to get that second layer over top. I put a little animation up on the screen to show you what it would look like if we cut away the side of that furnace that Declan's inside to right now. See inside of it. This is what it would look like. It would be a large ceramic pot. You put your pipe in there, you turn in one direction, and the glass winds up just like honey on a honey dipper. Then we have that second layer of glass on there, double or sometimes even triple the amount of glass in the end of that pipe. We go ahead and use that block tool. Again, this one's just a little bit bigger. Same material, same concept. We're shaping this up, getting a smaller piece. This step is much like centering a piece for a ceramic centering it on the wheel. Centering it on our axis right here. Dipping that block in the water as needed to not leave any residue on the surface of the glass to make sure we're not burning away too much of that block.
देखिए यूट्यूब फैमिली, यहाँ पे हम लोग लाइव बना रहे हैं. ये ग्लास वेस बन रहा है. यहाँ कॉर्निंग म्यूजियम में
glass changes in direction, changes temperature in either direction too quickly, we are at risk for thermal shock, which means it would crack or break. As glass cools, it constricts, and as it heats up and expands, that's what causes the cracking and breaking. This tool right here is called the jacks. The jacks are two dull blades attached to a spring mechanism. We use those two dull blades for closing and opening things, and now we're closing something to make a constriction line right at the head of the pipe. Seems like we might have pulled a little bit of a neck here, and then we're doing another constriction line right at the head of the pipe. That actually is going to be the line that creates a weak point. Going right at the head of the pipe. That's where we're going to tell the glass to break. Functions just like a score mark on a candy bar to break it, just to fix that weak point. Tell the material where to break. If you've ever broken glass before, you know it doesn't always go according to plan. So you kind of have to give it as much encouragement as possible to ensure a successful result. Now we're always fighting gravity, but for just a second we're using gravity to our advantage to stretch out this piece. The glass we're using today is called soda lime glass. It gets its name from the two added ingredients. The base is silica sand, which is the base of all glass. And then the added ingredients are soda ash and limestone. Soda ash is the flux, which means it's the ingredient that's added to make it melt at a lower temperature. This glass melts about 2,000 degrees. Just pure silica sand would melt about 4,000 degrees. And then limestone is the stabilizer. use all these ingredients up ourselves. The manufacturer that does it for us, they ship it to us. That process can be pretty tricky, a little bit dangerous. We let them do that for us, they're very good at it. And they send us something like this. This is called batch. It's a pelletized batch. This is what we load into our furnace. It's a little bit safer for us than powdered materials. When we load into our furnace, it doesn't aerosolize as easily. We load it in there, we turn the furnace up a little bit, we bake it for 8 hours, a little bit more sometimes, and then we stir it around. We have our beautiful clear glass that we're working with today. And we're not using any color in this piece. This piece is completely clear. We didn't use color, we use something like this. This is frit. F-R-I-T, frit. It's little tiny pieces of glass, little shards. They're super, super rich and dense in color. We would have done it at the very beginning. We would have rolled the piece in the color. Coat the surface just like rolling an ice cream cone in sprinkles. The way that color is made, we don't make it here either. We buy it from a company that sells it online and ship it to us. The way that it's made is with something like this. This specifically is iron oxide, rust. Different metals or metal oxides make different colors. And if I poured this into our furnace, we're going to make all that clear glass, and turn all the glass in there. This beautiful shade of green. There's lots and lots of different colors that we can buy. Lots of different mixes. Some of them we know. Cobalt makes this beautiful cobalt blue color. Manganese makes purple. Copper makes that beautiful light blue color that's down on that glowing table picture. And gold makes pink. So we like pink or red glass. Do you have very expensive taste? Gold can be a little bit more expensive, especially in terms of glass color. Just refining the shape a little bit more, going back and forth between heating, shaping. We're adding a little bit of air as well. That tube that's connected to the end of the whole pipe is actually adding air and inflating this a little bit as we go. When we had to blow glass with masks on, that made it a little bit difficult. We had to figure out a way to be able to do it. So we created this little tube thing that's connected to the little pipe. That tube is connected to a foot pedal, and when the foot pedal is pressed, it delivers about 1 to 2 pounds of air pressure into the pipe. Traditionally, there would be a person waiting for Declan's cue to add air to the piece. So Declan's been pretty self-sufficient up until this point, but now we need a little bit of help from Diego. It becomes fairly obvious why it's important to have an assistant for this process. It's a lot easier to have that extra set of hands while you're working with these pieces, especially when you're adding a piece to the bottom. You need keep both pieces turning and using the tool at the same time. Declan just doesn't quite have enough hands for that. Not yet. Now this part of the process is a little bit more nerve-wracking. We're going to flip this piece around. We finished with the bottom and we flip with the piece. We want to let that harden up, but we still want to work on the mount of the piece. And that mount is connected to the pipe. So we're going to flip this all the way around. We're going to use this piece of glass that Diego has created. That's called the punty. That's just the technical term for that transfer rod. We center it on the piece. And then just as I will use some thermal shock on that constriction point that I was talking about earlier, and we'll break the piece free. We'll be able to work on the other side. was working to steal heat from the puntee because you want it to be a temporary connection. You don't want it to be a permanent connection. Eventually, you want this piece to come off of the pipe. But if it's too cold, then it could just fall off from that vibration of the shock. It could go all the way through the piece, fall off both sides. Or if it's too hot, it can kind of flop around and not be very manageable. This is a Goldilocks temperature for sure. We're making a few adjustments to the puntee placement here. And then we're going to go back to that heat. That glass is sharp if it's cold enough to break, it's cold enough to be sharp. So we're melting down the sharp edges and then we're bringing it back up to working temperature. It's all the way into the reintroduce heat back into the back end. Even though we don't want that to be moving, we still want to make sure we're reintroducing heat back there. If it's left out in the open air, it can cool down too quickly and crack back there. If that cracks, it will most likely crack on that temporary connection. I'm going to play a video here and talk a little bit about what we're going to do at the end of this process. So every piece we make in here, we have to put in our annealing ovens. If we left this piece out in the open air on this table here to cool down, it'll take about 3 minutes and the piece will crack and then eventually explode. We don't want that to happen, so we're going to put it in one of our annealing ovens on either side of here. Those annealing ovens are set to about a 12-hour cycle. It keeps the entire piece the same temperature for each step of the process. Brings it down slowly, releases all the stress out of that piece so that tomorrow morning when we open up our annealers, we can handle all of our pieces and be sure that the stress is they're all stress-free. These pieces only need 12 hours, which we do get a little bit impatient. We want to look at our pieces right away. But we like to remind ourselves that 12 hours isn't too much. We can really just go home and come back tomorrow morning and get to see them. There's a lot of thicker pieces in our collection, and those thicker pieces need a lot longer. There's some pieces in our collection that have been pulled for 6, 8, maybe 12 months. It's a long, long time. Once you put those pieces in the annealer ovens and you press that cycle, you can't open them up to look at them or even check them to make sure everything's going okay. You have to wait the entire duration of the cycle before you can open those machines back up. So we've done some trimming on the lip of this piece. There's also some non-verbal communication to be very aware of where they are in the space. It's important to ensure the success of the piece that you're communicating the entire time with your assistant or with your gaffer. It's also important to be paying attention to where your person is for safety reasons, things like that. Diego's going to shape up a handle here. It's Diego's job to make Declan's life as easy as possible, so Declan can just focus on their piece. Getting a slight tapered shape. Keep this piece of glass. We'll be able to attach the two together. Handles are pretty difficult. They can be pretty tricky. Shaping a handle sometimes is just like shaping a wet noodle. We've got that pour spout on there, so we'll put that handle directly opposite of the pour spout. Signals to straight up and down, and right, directly opposite. I snip it right off, it's the easy part, and then here comes the hard part. Getting the right temperature, working with the super hot glass. Beautiful. Beautiful application, right? Shaping it up a little bit, a couple extra seconds, but I'll reintroduce it to the heat just a second to make sure that the hot handle doesn't shock the cold piece of the glass. And when I say cold, I mean about 1,000 degrees. About 1,000 degrees is where glass stops moving, and then about 950 is where glass is at a critically cold temperature, where you're worried about shocking the glass. So there's not a large margin for error there. We want to make sure that we're keeping it always about 1,000, no lower than that. And we've come to the end of our piece. One last time we'll use thermal shock to break the piece right out of being empty. Water right on that temporary connection. And then this tap that comes right off. Go towards the bottom. Anything cold enough to break, so cold enough to be sharp, and then make sure we melt those sharp spots off. And then one last look, and away in the annealer it goes. Now that it's safely away in the annealer, we are good to let it cool down over the next 12 hours.
Thank you.
That brings us to the
Bye-bye.
end of our demonstration.